Hello everyone and welcome back to this Nanophotonics and Plasmonics course. If you're still watching those videos, it means that you've reached a significant milestone as we are entering now the second half of the course, which will focus on Plasmonics. And to start with this new topic, we will start discussing surface plasmons, which is just a specific case of electrodynamics in noble metals. So first of all, let's try to spend some time on redefining what plasmonics is. So plasmonics is the interaction of light with metals. So this is a resonant behavior, a resonant interaction between electromagnetic waves and the conduction electrons in metal, more specifically. So plasmonics is a multidisciplinary field which is at the interface of quantum mechanics, solid-state physics, nanotechnologies, wave optics, and also chemistry. So it's a very rich field, as you will see in the next series of lectures. So this resonant behavior occurs when light is at the frequency which is resonant with the natural frequency of collective oscillation of the electrons in the metal. So these are just listing, very broadly speaking, some of these applications we're going to cover. So from subdiffraction limited optics to sensing applications or surface enhanced optical spectroscopies. There's going to be also some applications in solar energy harvesting, especially in photovoltaics. Medicine also takes advantage of plasmons, especially for therapies and drug delivery, but also for imaging, wave guiding, optoelectronics, and overall integrated circuitry. I've also benefited from plasmonics, and then toward more chemistry, catalysis, and in general the concept of sustainability have already exploded over the recent years, thanks to the development of new plasmonic materials, and of course the development of new optical media and materials that can be used for any type of applications, from new screens to smart windows. So let's go back a little bit in history and try to discuss the discovery of plasmons. So we briefly discussed that in the first chapter, but I wanted to provide a one-slide summary of the history of plasmons, starting with the pioneering work by David Pines and David Bohm, who predicted theoretically the existence of such a plasmon. So they introduced the concept of plasmon. We're talking about the bulk plasmon. So this is the plasmon in bulk materials. We're going to discuss what that means later on. Those plasmons have been observed experimentally by Hiroshi Watanabe at Hitachi Research Labs just a couple of years later. The year after Watanabe's experiments, Rufus Ritchie at Oak Ridge National Lab wrote a theoretical paper predicting the existence of surface plasmons. So now we are not discussing about the bulk plasmon, but the surface plasmon. So this is something that derives, of course, from the bulk plasmon, and we're going to discuss extensively the relationship between those two. So this particular chapter will focus on those surface plasmons. So the experimental observation of those surface plasmons has been fairly soon after, in 1959, by Cedric Powell and John Swan, University of Northwestern Australia. So where they observed experimentally using electron energy loss spectroscopy those surface plasmons. So we'll discuss some of these works later on when discussing about the physics of those plasmons. We're going to be discussing also about electron energy loss spectroscopy. So we come back to those pioneering works. So let's focus for a second now on what are the plasmonic materials. So the best plasmonic materials, the ones that are very standard, often used for applications, but also for fundamental research purposes, are typically noble metals such as copper, silver, and gold, but also aluminum. So aluminum has been shown to be a great plasmonic material in the mid 2010. So there's been additional work as well exploring new type of material that can exhibit plasmonic properties. I'm not going to discuss that for the moment here. I can just mention one of them, which is magnesium. that have been shown to exhibit interesting plasmonic properties. So you can achieve also plasmonic properties from very heavily doped semiconductors, which is beyond the scope of this lecture. So let's focus on those four major plasmonic elements: aluminum, copper, silver, and gold, and look at the origin of these plasmons. So if you want to understand the optical properties of these plasmons, you need to understand where the plasmon come from, and this you need to go back to the electronic band structures in those metals. So these are the electronic band structures for gold, copper, silver, and aluminum. So there are a few things that we can notice here. So that there's a very dense region where you have a lot of D bands that are formed. Those D bands are the valence bands of those metals. They are way below the Fermi energy, which is shown by this dashed line here. So they're typically 2 electron volts below the Fermi energy. Now, starting below the Fermi energy all the way up, we have those S and P states that are actually hybridizing, forming those SP bands. Those SP bands that are shown in all 3 metals are actually the conduction bands of those metals. So the existence of those conduction bands below the Fermi energy is the reason why those conduction electrons can actually be excited and oscillate. So what we can see as well is that the density of state, the density of electronic state below the Fermi energy is very significant for all those 3 metals. We have a very large density of state in the valence band. The conduction band is much smaller density of state, and it's more broadly distributed in energy as opposed to the density of state of the valence band. Something which is also interesting to mention is that aluminum is actually exhibiting a fairly different electronic band structure compared to the other 3 metals. So something which is very important to notice as well is the number of conduction electrons that are present in those different materials. So if you go with copper, gold, and silver, there's only 1 conduction electron per atom. So there's only 1 S electron present in this conduction band, as opposed to the aluminum. So these are the electrons that are going to contribute to the plasmon oscillations. So you see that for aluminum we have 3 conduction electrons. So there are 2 S electrons and 1 P electron that contribute to this plasmon oscillation, and that's going to explain the very high energy and the very strong plasmonic response of aluminum as compared to the other 3 noble metals. So let's go back to Maxwell's equations. So surface plasmons are electromagnetic surface modes. They are solutions of Maxwell's equations. So if you want to calculate the plasmonic properties of a metal, looking at how this metal reacts when illuminated by an external electromagnetic field, you need to solve Maxwell's equations. So you need to use the 4 fields: electric field, electric displacement, magnetic field, and magnetic inductions, along with the polarization and the magnetization. So electric fields, magnetic fields, electric displacements, and magnetic inductions are connected to the polarization and magnetization. So if you look at the electric displacement, that's now the physical quantity, which is important because it contains the response of a free space when an external electric field is applied, and as well as the response of the material itself. The same for the magnetic component, but we not discuss the magnetic behavior of those materials as they are generally non-magnetic. So because we are dealing with matter, we also have to introduce the constitutive relations that we discussed in chapter 2. So the dielectric permittivity epsilon that we're going to be referring from now on is actually the relative permittivity, and it's a physical quantity that governs the metal behavior under an external electric field. So typically this dielectric permittivity is a complex quantity that has a real part and an imaginary part. We can also define the electric conductivity, surface conductivity, which is also a complex quantity, and those two physical properties are actually connected with this expression. So experimentally, the dielectric permittivity is usually determined via the complex refractive index. So we have a complex refractive index with a real part n, which is defined as a refractive index, and an imaginary component, which is this kappa function, which is the extinction coefficient. So the refractive index determines the speed of the electromagnetic waves within the medium, while the kappa determines the absorption of the electromagnetic wave in the medium, or how this electromagnetic wave will decay when propagating through a given medium. So those quantities are actually connected, so you can go back and forth between the refractive index and dielectric permittivity, so you have some useful relationship between the real part and imaginary parts of those two physical quantities. So let's now look at this dielectric permittivity or dielectric function in the case of a free electron gas. So the optical properties of metal, typically they can be described by a free electron gas model, so which is also known as a Drude-Sommerfeld model. So these free conduction electrons constitute a plasma. So this is a gas of charged particles that react collectively when you apply an external electromagnetic field. So if you consider that matter is composed of heavy positive ions, which are basically just the nuclei of the atoms with the protons, you can displace the electron gas, you can displace the conduction electron when you apply an external electric field. So you can really displace those negatively charged electrons with respect to the positive electron background. So then you end up with a polarized medium where you have positive charge and negative charge, and you're going to induce some electric dipole moment. So this can be described using an harmonic oscillator model that's basically known as the Drude-Sommerfeld model. So we can really look at how this mass, which is this collective oscillation of the electrons, oscillates back and forth when you apply an external force, and you have this restoring force, which can be just the Coulomb attraction between the electrons and the positive ion background. So you can actually look at this very simply as something you should know. Simple harmonic oscillator. You can write the equation of motion for this particular system for the electrons that are being accelerated. So we have this external electric force. So that's just the charge of the electrons times the electric field, which is a time harmonic electric field. And then we have some damping, which is the friction force. So that's basically the losses that are in the system. So we have this driving electric force, this friction that are contributing to the motion of those electrons. So we start with this equation of motion for the free electrons I just wrote before. You can solve this equation. I'm not going to detail the steps for that. You end up with solutions of this form. So you have the displacement of this mass, or those electrons in general, when you apply this external electric field, which is a function of time. The mass of the electron, you have this damping term, which is going to be giving you how this oscillation will be damped over time. And then you have the charge of the electrons. Remember, we have a Coulomb type of interaction between this electric field and the charged particles. So the displaced electrons, they contribute to a macroscopic polarization. I just discussed that we have this polarization that forms as a result of the separation of positive and negative charges. So this macroscopic polarization is just described by how many electrons you have that are being displaced. What's the charge of each in the electron? So you have the total charge which is being displaced times the actual displacement. So this displacement is what we just calculated, solving the equation of motion. So we can substitute this R in this expression, and you end up with the macroscopic polarization, which can be expressed as a function of the electric field, the number of electrons. So this is in fact the electron density, the charge of the electron, the mass of the electron. So knowing that the electric displacement is epsilon node times the polarization, then we can just rewrite this electric displacement this way. So we can just introduce this constant. So it's just putting together in this simple term here all the physical constants, such as the density of electrons in the conduction bands for this particular metal. So this is material dependent. It's going to be different for silver, gold, copper, or aluminum. This is the charge of the electron, the mass of the electron, and the vacuum permittivity. So this quantity omega p is known as the bulk plasma frequency. So this is a quantity which is material dependent. So because the electric displacement can be also written as epsilon node epsilon e, then if we just compare this expression we obtained before to this, then it's very straightforward to see that the epsilon is actually this quantity in the parentheses. So this is the Drude dielectric permittivity of this free electron gas. So we have 1 minus omega p squared, which is the bulk plasma frequency, over omega squared plus I gamma omega. So this Drude model is a very simple model. It's just a harmonic oscillator model, but it works extremely well for metals. And the reason why it works very well for metals is because the conduction bands of metals are actually parabolic. So if you look at the shape, the dispersion, the energy as a function of the k vector of the momentum of these conduction bands, you see that they are in fact very close to parabolic shapes, and that explains why the free electron model works very well. So if you remember your quantum mechanics course, you can go back to look at what a free electron dispersion looks like, and you're gonna end up with the energy which is proportional to the momentum squared. So that's exactly the case here. So that's why this free electron gas model works very well for metals. However, this is still an ideal model, and when the frequency is very large as compared to the bulk plasma frequency, then the value for epsilon actually tends to 1. So this is something which is not true. So that would mean that this is basically just a vacuum. So in fact, an extension is actually needed for noble metals when those the frequency is larger than the bulk plasma frequency. So the reason why is because in this region, when you have large frequencies, or basically large energies, the response is actually dominated by the s electrons. So we have the s electrons that are in the conduction band that dominate the response. So the d bands that are forming the valence band here at the very bottom below the Fermi energy, actually they create and contribute to a polarized environment. So you have to keep in mind that those electrons are here, and the positive ion background that we discussed before is actually screened by those d electrons. So we don't have only protons forming this positive background, but we have also those electrons that are also present. So we have to account for this polarized environment of those valence electrons and with the protons, and this is done via the introduction of macroscopic background polarization that accounts for these electrons. So we can just rewrite this macroscopic polarization this way with this additional dielectric permittivity that we describe how those valence electrons will react to electric fields, and that allows us to rewrite the Drude dielectric permittivity very, very similarly, but instead of having 1 here, now we have this epsilon infinity, which depends on the metal you're considering. So the collision frequency or the damping, this gamma term, can be calculated theoretically via the Fermi velocity and the mean free path of the electron. So this is basically related to electron-electron collisions as those electrons are oscillating collectively. So those electrons are going to start colliding, and the oscillation going to lose the coherence and the collectiveness, and that's basically going to introduce this damping term. So this effect of the interband transitions, or between basically the sp to d-band electrons, so that's very important. So we have to account for the electrons that are going from the sp band down to the d-band. So if you look at this, the example of silver, in bulk, the mutual polarization of the s electrons and the d electrons, it causes basically a screening of the bulk plasma frequency. So I'm not going to enter too much into the detail, but if you calculate the bulk plasma frequency for a pure free electron gas model, you're going to end up with 9.2 electron volt. But what is actually observed experimentally is a 3.76 electron volt. So this screening here is actually resulting from the contribution of the valence electrons to the optical response. That was not included in the free electron model. Correspondingly, we're going to discuss later about the surface plasmon frequencies. So the surface plasmon frequency is just the bulk plasma frequency divided by square root of 2. So this is also affected. So we have also a screening of this frequency. So the actual unscreened frequency for the free electron gas is about 6.5 electron volt for silver, and what is actually observed is a 3.64 electron volt. So this is something which is observed experimentally for silver. So to finish this video looking at the interband transitions, so if you actually want to include the interband transitions into the dielectric permittivity and account for that, you can do it via the Lorentz model. So as I just said, at high frequency, typically in the visible to UV range, the response of the bound valence electrons or the electrons from the D band are actually limiting the validity of the Drude-Sommerfeld model, which is accounting only for the conduction electrons. So how can we include the contribution of those D electrons? Well, you can do that basically by adding a restoring force and recalculating the response of those electrons. So you can calculate the response to an external electric field, the exact same external electric field of those valence electrons. So now we are looking at the valence electrons and no more the conduction electrons, and we can include this restoring force for those valence electrons. So we now introduce a new bulk plasma frequency type of quantity, which is very similar to what we introduced for the free conduction electrons. And you can solve this the same way, the exact same process as what we've done for the conduction electrons, and that's going to lead to the expression of these dielectric permittivity that will describe the contribution of this interband transition. So from the valence electrons. So you know, now we have a Lorentz function, so that's why it's the Lorentz model, which results from the introduction of this restoring force. And you can actually now extend the Drude-Sommerfeld model to a Drude-Lorentz model, calculate this overall dielectric permittivity that includes the Drude response and the Lorentz response from the valence electrons. So you can look at how this compares for gold and silver. So the black lines are actually experimental dielectric permittivities from Johnson and Christie, tabulated in 1972. We have the real part and imaginary part of those quantities. The green line is the Drude model only, so you see that it works fine for large wavelength or low frequencies. We have a very good overlap with the experimental dielectric permittivity, and as you increase the frequency or decrease the wavelength, you see that you deviate from those interband transitions that you see here. So we have this large contribution to the electric permittivity, which are the interband transitions, and the Drude model fails to describe this high energy region. So the same for silver in this particular region below 400 nanometers wavelength. Now the red curve is the Lorentz model only. So this is the interband transitions only. You see that we can just describe this Lorentz resonance that describes much better this high energy region. And if you calculate the Drude-Lorentz model, which is the sum of the two, the Drude and the Lorentz, you end up with the blue function here that describes fairly well this electric permittivity for both gold and silver.